You're sitting there, right, staring at your monitor, taking the AWS Certified Machine Learning Engineer Associate exam. The clock is just, ticking down.
Oh man, that clock is the absolute worst part.
It really is. And you read the scenario about processing a massive, messy data set. Your brain, which has been trained by years of hard-fought engineering battles, immediately screams, spin up a Spark cluster on Amazon EMR, write a custom script, take control of the compute.
Right, because that's the muscle memory. You want to build the hammer yourself.
Exactly. And the moment you select that answer, you've failed the question. Today, we're going to show you exactly why your finest developer instincts are actually your absolute worst enemy on this certification.
It is a brutal realization for a lot of senior engineers, honestly. I mean, you spend your entire career learning how to build and manage these highly complex infrastructure setups, and then AWS tests you on your ability to, well, put the hammer down and use a fully managed service instead.
Welcome to the Deep Dive. We are two cloud architects, and this conversation is custom-tailored specifically for you, the senior engineer, preparing for the MLA-C01. We are going to tackle what I consider the absolute elephant in the room of certification prep. If you go out onto the crowdsourced public forums to study, you are walking into a minefield of bad advice.
Yeah, the forum dynamic is fascinating, but it is incredibly dangerous if you're trying to learn the AWS well-architected way. You'll see developers out there fiercely arguing for, like, custom EC2 fleets, massive bash scripts, and heavy Hadoop ecosystem.
Because that's what they're comfortable with, right?
Exactly. But they are completely missing the native design patterns that the exam is actually designed to validate.
Right. So our mission today is a complete recalibration of your architectural compass. We aren't going to sit here and help you memorize a list of multiple choice answers. We are going to deconstruct the underlying systems engineering, WHY.
Which is the only way to actually pass the test.
Absolutely. We want to teach you how to analyze architectural constraints, focusing heavily on, SageMaker components, Amazon Bedrock, and AWS native data integration.
Right.
By the time we're done here, you're going to spot those legacy distractor answers from a mile away.
It's all about shifting your mindset, right? From how do I build this from scratch to how does AWS want me to orchestrate this with the least operational overhead?
Okay, let's unpack this. I want to start at the absolute beginning of the machine learning lifecycle, which is the data foundation. Because frankly, this is where the do-it-yourself instinct is the most overpowering.
Oh, for sure. Data engineering brings out the control freaks in all of us.
It really does.
Yeah.
So let's put ourselves in the shoes of an engineer facing a classic scenario. You are building a fraud detection model. You have gigabytes of transaction logs and customer profiles sitting in Amazon S3.
Standard setup so far.
Right. But because enterprise data is never clean or localized, you also have critical customer relational tables sitting in an on-premises MySQL database. The data is heavily siloed.
A very realistic, highly stressful engineering problem. I mean, you cannot train a model on fragmented data.
Right. Now, you look at the study forums for this exact scenario, and the community is practically at war. Half the people are screaming, Amazon EMR, use Apache Spark to ingest the MySQL data and join it with S3.
And the other half?
The other half are arguing for custom Python scripts running on massive EC2 instances. Now, if I'm a big data engineer, EMR is my comfort zone. Why is that the wrong answer here?
It's the wrong answer because it fundamentally mistakes a raw compute engine for a centralized aggregation and data governance service. Let's really break down the mechanics here.
Yeah, please do.
EMR with Apache Spark is an incredibly powerful tool for heavy distributed data transformations. If you need to write complex MapReduce logic to process petabytes of unstructured text, EMR is fantastic.
It's a beast.
It is. But look at the constraints of the AWS well-architected framework, and specifically how these exam questions are phrased. They almost always revolve around the phrase minimizing operational overhead.
And EMR has a massive operational footprint. I mean, it's huge.
Exactly. Think about it. If you choose EMR, what have you just signed up for? You are now responsible for cluster provisioning. You have to select the right EC2 instance types for your master and core nodes.
You have to manage the EMR versioning.
Handle scaling policies, right. And crucially, you have to write custom PySpark or Scala code just to establish the connection between S3 and your on-prem MySQL database. You are managing infrastructure just to join two datasets.
So my developer instinct to write code and manage clusters is actively hurting me here. What is the native AWS solution that I'm, supposed to be seeing?
The native solution is AWS Lake Formation. And what's fascinating here is that lake formation isn't a compute cluster you manage. It's a managed service explicitly designed to build, manage, and secure data lakes.
Okay, so it's doing the aggregation for me.
Right. Its entire purpose is to aggregate data from disparate sources like your S3 buckets and that on-prem relational database into a central searchable catalog.
Wait. How does it physically connect to the on-prem database without me writing a Spark job to pull the data? Like, how does the data actually move?
So, under the hood, lake formation utilizes AWS Glue blueprints and crawlers. You simply configure a blueprint pointing to your JDBC connection for the MySQL database.
Oh, so it's just a configuration step.
Exactly.
Hmm.
Lake formation automatically generates the underlying Glue ETL jobs to ingest that data into your S3 data lake, and it catalogs the metadata. It handles the cross-source aggregation natively.
That's wild.
Yeah, you don't manage the servers executing the job, and you don't write the data movement scripts. EMR is the distractor because it preys on your muscle memory as an engineer,
Yeah.
completely ignoring the managed abstraction that AWS provides.
That makes a lot of sense. You're trading infrastructure management for configuration. Okay, so we've used lake formation. The data is now centrally located. But we have another massive problem.
The data is dirty, isn't it?
The data is filthy. Our scenario dictates that we have categorical data-like strings of text for city names that needs to be converted to numerical data for our algorithm.
Standard encoding stuff.
Right. But more importantly, we have a massive class imbalance. It's a fraud detection model. In the real world, maybe, 99.9% of transactions are perfectly legitimate and 0.1% are actual fraud.
This is literally the bane of every machine learning engineer's existence. I mean, if you feed a 99.9% imbalanced data set into an XGBoost model, the model takes the lazy route.
It just guesses not fraud every time.
Exactly. It just learns to guess legitimate every single time. It achieves 99.9% accuracy and is completely mathematically useless for detecting fraud.
Completely useless. So we need to fix the imbalance, and the exam asks us to do it with the least operational effort. Now, on the forums, the heavy code engineers suggest using AWS Glue to write a custom ETL script, or using a SageMaker processing job with a custom Python script, utilizing the imbalanced learn library to handle the oversampling.
And they love defending that approach.
They really do. But the well-architected answer is Amazon SageMaker Data Wrangler. And honestly, I have to push back here a little bit.
I welcome it. What's your hesitation with Data Wrangler?
My instinct as a Python developer is that I want robust, version-controlled pipelines. Isn't Data Wrangler just a point-and-click UI?
It is a UI, yes.
Right. So if I'm building an enterprise-grade ML pipeline, I cannot rely on someone manually clicking buttons to balance a data set. Why wouldn't I just write a robust Pandas or Spark script in Glue? How is a UI the right answer for an enterprise architecture?
It's a very common bias, and it's exactly why senior engineers get tripped up on the MLA-C01. We vastly prefer code to clicks. We want everything in Git. But if we connect this to the bigger picture, Data Wrangler is not just a simplistic UI that disappears after you use it.
Okay, what is it then?
Think of Data Wrangler as a visual IDE for data engineering, backed by a managed supercomputer that outputs infrastructure as code.
Okay, outputs infrastructure as code is the key phrase there. Explain how that works.
When you use the Data Wrangler interface, you aren't just altering data in memory on some random server. You are visually constructing a data processing directed acyclic graph.
So it's building the pipeline steps in the background while I click.
Exactly. For your categorical data, you don't write the boilerplate pandas code for one hot encoding or ordinal encoding. You select it from over 300 built-in transformations.
And what about the fraud class imbalance? That's heavy math. That's not just replacing a string with an integer.
Right, and that's where the managed aspect really shines. Data Wrangler has a specific balanced data operation built right in. You don't have to manually code a technique like SMOT, the synthetic minority oversampling technique.
Let's actually pause on SMOT for a second, because understanding the mechanism helps explain why we want to offload it to AWS. What is Smoke mathematically doing under the hood that would be such a pain for me to code from scratch?
Okay, so SMOT doesn't just duplicate your existing fraud records, right? Because if you just copy and paste the same 0.1% over and over, that would lead to terrible overfitting.
The model would just memorize those specific transactions.
Exactly. So instead, SMOT synthesizes entirely new, mathematically plausible data points. It takes a minority data point, a known fraudulent transaction, and plots it in high-dimensional feature space.
Okay.
Then it finds its k-nearest neighbors, meaning other similar fraudulent transactions that are close to it in that multidimensional space. It literally draws a line in that mathematical space between the original data point and its neighbors and randomly places a brand new synthetic transaction along that line.
Wow. So it's dynamically generating new data based on the Euclidean distance between existing features.
Precisely. It's generating data that is statistically consistent but entirely unique. Now imagine writing the Python code to manage those distance calculations, the neighbor counts, and the distributed compute required to run that math across terabytes of data in a Spark cluster.
Yeah, that's incredibly high operational overhead. You'd spend a week just optimizing the PySpark job to not run out of memory.
Exactly. Data Wrangler abstracts all of that into a configuration step in the UI.
But coming back to my original pushback, how do I automate that if it's just a UI? I still don't want to be clicking buttons in production.
And you don't have to, because once you visually verify that the Sentmo transform worked on your sample data, Data Wrangler allows you to export that entire visual flow into a JSON recipe.
So it creates an artifact.
Yes, that recipe natively integrates into a SageMaker pipeline or can be exported as an AWS CloudFormation template. It compiles your clicks into an automated SageMaker processing job that runs headlessly in production.
That's amazing.
Yeah, you get the speed of visual feature engineering with the rigor of automated version-controlled pipelines. That is why it is the least operational effort answer.
Okay, you've completely convinced me. The abstraction doesn't sacrifice the engineering rigor, it actually enhances it. Let's move to another data nightmare that really highlights this code versus managed service battle. Unstructured duplicates.
Oh, this is a classic trap. I see this all the time.
Here's the setup. You have a massive, highly unstructured data set. Let's say it's a CRM database spanning a decade. You have severe duplicate record issues across several key attributes. You have John Doe at 123 Main Saint in one row, and Jonathan Doe, 123 Main Street, apt B in another.
Same person, different formatting, terrible data hygiene.
Exactly. And if you look at how developers try to solve this on the internet, the suggestions are wild. Because the word unstructured is used, people panic.
They really do. You will literally see recommendations on forums to use Amazon Mechanical Turk to crowdsource human workers to manually read and find the duplicates.
Which is financially and operationally insane for terabytes of data. You can't pay humans to read 1 million rows of CRM data.
Completely insane. But the more common engineering trap is developers saying, oh, I'll just write a Python script using Levenshtein distance to calculate string similarity, and I'll run it on an EC2 instance.
Right. That's exactly what my instinct would be. I'd write a fuzzy matching script using some open source library. Why is that a bad idea?
Think about the computational complexity of what you're proposing. If you have 1 million rows and you need to compare every row against every other row to find fuzzy matches, you are looking at an O(n)² algorithmic complexity.
That's a lot of comparisons.
It's 1 trillion comparisons. Your Python script on a single EC2 instance is going to melt the CPU and run for weeks. You would have to build a highly optimized distributed Spark job just to handle the string matching without crashing.
So what is the native AWS service that bails me out of writing distributed string matching algorithms?
It is the AWS glue find matches transform. And this is a brilliant piece of engineering that often gets overlooked by test takers.
Wait, find matches, is that a separate service?
No, it's not a standard standalone ETL tool. It is a purpose-built machine learning transform operating within AWS Glue.
Oh, so it's ML doing data prep for ML.
Exactly. AWS has already trained a complex ML model under the hood to recognize fuzzy matches, typos, phonetic similarities, and structural variations in messy data sets.
So I don't have to write the matching logic at all. I'm basically using a pre-trained ML model to clean my data for my actual ML model.
Yes. You provide find matches with a small sample of what you consider a match and what you consider not a match, so it learns your specific business logic. This is basically active learning.
Right, you're fine-tuning its understanding of your data.
Exactly. And then it scales out across the Glue serverless infrastructure to process the terabytes of data. You write virtually zero code compared to building a custom deduplication model from scratch.
This raises an important question, though. We just established, like 5 minutes ago, that Data Wrangler is the go-to for data preparation. Why are we using Glue here instead of Data Wrangler?
It comes down to the specific capability constraint. Data Wrangler is incredible for feature engineering and coding, scaling, balancing, all that tabular math, but it does not have a native built-in ML algorithm specifically dedicated to fuzzy string matching across unstructured rows.
I see.
Glue find matches is a specialized tool for that exact deduplication problem. The exam tests your ability to pick the right specialized tool for the specific data anomaly. You can't just apply Data Wrangler to every single problem.
Okay, that distinction is crucial. You have to know the boundaries of these services. Let's hit one final data foundation scenario before we move on to the actual training phase.
Let's do it.
Imagine you need to process thousands of existing CSV objects in an S3 bucket. Let's say they are daily sales reports. New ones are being uploaded constantly. They all share the exact same schema, and one of the columns is a transaction date.
Okay, pretty standard data lake setup.
Right. Your only requirement is to query this massive pool of CSVs based on that specific date with the absolute lowest operational overhead.
The reflex for most data engineers is to build a standard ETL pipeline. They think, I need to query this fast, so I should convert these CSVs to Parquet, partition them by date, and store them in a new bucket.
Right, because Parquet is columnar and way faster to query than flat CSVs.
Exactly. So they set up an AWS Glue Apache Spark job, write the transformation logic, manage the execution, write the output to a new S3 location, and set up a crawler.
But the scenario just asks to query the data. It didn't say anything about building a permanent data warehouse or setting up a daily batch job.
Precisely. The ETL pipeline is massive over-engineering for the stated constraint. The well-architected solution here is Amazon Athena, specifically utilizing a CTAS statement that stands for Create Table as Select.
Explain the mechanics of Athena and why it wins on operational overhead here. Because normally I think of Athena as just an interactive query tool, not a processing engine.
That's a common misconception. Athena is a serverless query service built on Presto, which is a highly distributed SQL engine. It allows you to query data directly in its raw form in S3 using standard SQL. You don't need to load the data into a database first.
Okay.
By executing a CTAS statement, you can tell Athena, run a SQL query against these raw CSVs, filter by the transaction date, and automatically write the results of that specific query into a new optimized table in S3.
Wait, so the query itself performs the transformation and the storage routing in one serverless execution?
Yes. You don't manage a Spark cluster. You don't write ETL code in Python. You write one line of SQL. Athena spins up the compute in the background, executes the query in parallel across the thousands of CSVs, writes the result to S3, and spins down.
That's incredible.
It is instant, it's serverless, and it perfectly matches the least overhead constraint. You literally just pay for the data scan during the query.
Okay, to summarize this first phase, your developer instincts are going to scream at you to write custom code, manage clusters, and build complex pipelines. You have to fight that urge.
You really do.
Look for the managed abstraction, lake formation for cross-source aggregation, Data Wrangler for feature engineering and SEMO balancing, Glue find matches for fuzzy deduplication, Athena CTAS for serverless S3 querying.
If you master those distinctions, you will absolutely breeze through the data engineering domain of the exam.
But eventually we have to actually train a model. We have to feed this beautifully prepared data into a GPU. And this is where architectures absolutely fall apart.
Oh, they really do.
Right.
The physics of cloud storage and network I/O are deeply, deeply misunderstood by a lot of ML practitioners.
Let's lay out the scenario. You are training an image classification model. You have millions of small files. Let's say they are high-res images, maybe 2 to 5 megabytes each. They're sitting perfectly in an S3 bucket.
Okay.
You spin up your SageMaker training job, utilizing a massive, expensive P40 instance with multiple GPUs. You start the training and you look at your CloudWatch metrics. Your GPU utilization is sitting at 10%. The training is taking forever. The GPUs are just idling.
And this is where the panic sets in, because you are burning thousands of dollars an hour.
Yes. So you go to the forums, and people are offering desperate, hacky solutions. They suggest copying all the millions of images to an Amazon Elasticache Redis cluster to speed up read times. Or they suggest writing pre-processing scripts to bundle thousands of images into massive tarball files before the training job starts to reduce the file count.
Both of which are terrible ideas. Let's diagnose the illness before we prescribe the cure. Why is S3, which is the backbone of AWS, failing so miserably here? What is mathematically happening that is starving the GPU?
Yeah, explain that, because S3 is supposed to be limitlessly scalable.
S3 is a phenomenal service for total throughput and limitless capacity, but we have to remember what it actually is mechanically. It is an object store accessed via REST APIs over an HTTP network.
Right.
When your training script asks S3 for a file, it isn't just reading a sector on a hard drive. It is initiating a TCP handshake, sending HTTP headers, waiting for routing, and downloading the payload.
And doing that for a massive 100-gigabyte file is fine because the overhead is minimal compared to the payload. But doing it for a 2-megabyte file?
Exactly. When you have millions of tiny files, the The latency overhead of initiating millions of individual HTTP GET requests completely overwhelms the network layer.
So it's the handshake that's killing you, not the data transfer.
Yes. The time spent negotiating the network requests vastly exceeds the time spent actually transferring data. Your tens of thousands of dollar GPU is literally just sitting there, twiddling its thumbs, waiting for the network card to finish talking to S3. The math of HTTP overhead breaks the architecture.
Okay, so why not use Elasticache Redis? It's an in-memory data store. It's blindingly fast. Why is that a bad forum answer?
Because Redis is an in-memory key-value store designed for microsecond caching of database queries or session state. It is not a PCX-compliant file system designed to stream terabytes of unstructured image data to a training algorithm.
Oh.
Storing millions of 5 MB images in RAM across a Redis cluster would be astronomically expensive and architecturally inappropriate. You'd spend a fortune just to hold the data in memory.
So what's the well-architected solution that solves the HTTP bottleneck without bankrupting the company?
Amazon FSx for Lustre. If we connect this to the bigger picture, Lustre is an open-source, high-performance parallel file system that has been the backbone of supercomputing clusters for decades. It is designed specifically for high-performance computing and machine learning workloads.
How does it physically integrate with SageMaker and S3 to solve the bottleneck? Like, do I have to manually copy the data from S3 into Lustre?
No, and that's the beauty of it. When you configure FSx for Lustre with your SageMaker training job, you natively link it to your S3 bucket. Behind the scenes, FSx acts as a massively parallel high-speed cache. Crucially, it decouples the metadata from the underlying object storage.
What does that mean, practically?
It reads the directory structure of your millions of files from S3 and presents it to your SageMaker training instances as a local POX-compliant file system.
POX-compliant, meaning the training script just sees it as a normal local hard drive. It just uses standard Python open commands.
Exactly. The training script doesn't know S3 exists. When the script requests an image, FSx streams the data from S3 into its high-speed NVMe storage layer using massive parallelism, bypassing the individual HTTP GET bottleneck.
So it lazy loads the data, but does it in parallel?
Yes, it feeds those millions of small files directly into your GPUs at sub-millisecond latencies, keeping the GPU saturated at 90–100% utilization. You get the infinite scale of S3 combined with the blazing local file system speed required by deep learning.
That is such a vital mechanical concept to understand. Do not bundle tarballs. Do not cache in Redis. Use FSx for Lustre to break the I/O bottleneck.
Always look for FSx for Lustre when the exam mentions millions of small files or I/O bottlenecks.
Well, let's talk about a different kind of bottleneck.
Yeah.
Developer velocity and infrastructure startup time.
Oh, this is a huge pain point for MLO.
You are an ML engineer experimenting with a complex model. You tweak a hyperparameter, you launch the SageMaker training job, and then you sit and wait. You wait for the EC2 instance to provision. You wait for the Docker container to pull from the Elastic Container Registry. You wait for the data to download. It might take 5 to 10 minutes before the training even begins. You realize your learning rate was wrong. You kill the job, change the parameter, and you have to wait another 10 minutes for the infrastructure to spin up again. It destroys your workflow.
It completely breaks your flow state. If you look at the community advice for this, you'll often see people pointing toward managed spot training. They see the word managed and assume it's the AWS preferred way to optimize jobs.
But spot instances don't speed things up, do they?
No, in fact, they can do the exact opposite. Spot instances allow you to bid on spare AWS compute capacity for a massive discount. They are incredible for cost optimization on long-running, flexible jobs.
Right, if you don't mind the job being interrupted.
Exactly. But if capacity isn't immediately available, your job will sit in a pending state until a spot instance frees up. It's the exact opposite of what you want for rapid experimentation.
The actual architectural solution the exam is looking for is SageMaker Managed Warm Pools.
Correct. Let's look at the container lifecycle. Normally, when a SageMaker job finishes, AWS immediately tears down the underlying EC2 instance and destroys the container to save you money.
Which is great for cost, but bad for the next job you run 2 minutes later.
Right. But when you enable a managed warm pool, you define a time to live, say 30 minutes. When your training job finishes, SageMaker keeps the compute instances and your specific Docker container in a ready state for those 30 minutes.
So the heavy lifting is already done.
Exactly. The EC2 instance is already provisioned, the container image is already downloaded and running, the network interfaces are attached. If you launch a consecutive job with your tweaked hyperparameter within that 30-minute window, SageMaker simply routes the new job to the warm infrastructure.
And the startup time drops to what?
It drops from minutes to mere seconds. You iterate incredibly fast, and you only pay for the compute while it's active or being held warm.
It's a simple configuration change that drastically alters developer velocity. That's a great tip. Let's shift gears slightly and talk about the algorithms themselves. Because choosing the right built-in algorithm is a major theme on the MLA-C01, and developers bring a lot of outside bias into this.
They absolutely do.
Let's go back to our fraud detection model.
Yeah.
We have tabular data. It's a binary classification problem. Is it fraud or is it not? You go to the forums, and everyone is voting for LightGBM. They say, I use LightGBM for all my Kaggle competitions. It's the fastest, most accurate tree-based model for tabular data.
And, they aren't necessarily wrong about LightGBM's performance in the real world, but they are failing to read the exact constraints of the certification question. The prompt almost always specifically asks for an Amazon SageMaker built-in algorithm.
This is a semantics trap. LightGBM isn't built in.
Not in the specific way the exam defines it. You can absolutely run LightGBM on SageMaker. You can bring your own Docker container, or you can use a pre-built framework container and supply your own LightGBM training script. But it is not categorized as one of the native, out-of-the-box SageMaker built-in algorithms.
The built-in algorithms are the ones where AWS has written highly optimized, distributed implementations that you can just call via an API without writing the training loop.
Exactly. So if the exam asks for a built-in algorithm for a tabular classification problem, the native choices provided directly by AWS are XGBoost or Linear Learner.
Let's focus on Linear Learner because it's uniquely positioned. What makes it a good native choice over just bringing a custom script?
Linear Learner is purpose-built by AWS to handle both regression and classification problems on massive datasets. What makes it powerful is that it abstracts away the distributed training mechanics,
Which are usually a nightmare to code.
Totally. If you use a custom script, you have to manage how the data is sharded across multiple GPUs and how the gradients are synchronized across nodes. Linear Learner handles distributed stochastic gradient descent natively.
Nice.
Furthermore, it automatically trains multiple models in parallel with different L1 and L2 regularization hyperparameters and automatically selects the most optimal model for you. It is the epitome of least operational overhead for baseline classification.
Always pay attention to the exact wording. Built-in means AWS's prepackaged algorithms. Framework means bringing your own script to a managed container.
Exactly. Don't let your Kaggle experience override the AWS vocabulary.
Okay, let's zoom out. We've prepped the data, we've fixed the storage bottlenecks, we've trained the model. Now we enter the orchestration phase, MLOps. This is where the concept of glue code, and I mean lowercase g here, like custom integration scripts, really trips people up.
Oh yeah. MLOps on AWS is an exercise in ruthless abstraction. The less state management code you have to write and maintain, the more resilient your architecture is.
Let's lay out the scenario. You have an AWS glue workflow. Let's say it's executing that heavy ETL process every night to prepare incoming data. You need the output of that glue workflow to immediately feed into Amazon SageMaker pipelines, which will orchestrate the model development, training, and evaluation steps. You have two distinct, powerful AWS services. How do you orchestrate the handoff between them?
If you ask a traditional cloud architect, someone who comes from a microservices background rather than pure ML, they will instinctively reach for AWS step functions.
Which is an amazing service. It's a visual state machine. I use it all the time.
It is an incredible service. They think, I have service A and service B. I need a state machine to orchestrate them. So they design a step function that triggers the glue job, enters a wait state, periodically checks the glue API to see if it's finished, and upon success, triggers the SageMaker pipeline.
Right. I've built that exact architecture. It works perfectly. Why is it a trap on the exam?
Because while it works, it introduces unnecessary architectural complexity and violates the least operational overhead rule. You have now introduced a third service step functions, solely to manage the state of the first two.
Ah, is it?
You have to write the Amazon state's language definition, manage the IAM permissions for the state machine, and pay for the state transitions. It's extra overhead.
So what is the well-architected native ML solution that removes step functions from the equation entirely?
It is using callback steps natively within SageMaker pipelines. SageMaker pipelines is fully capable of pausing and managing its own state.
Walk me through the mechanics of a callback step. How does SageMaker talk to Glue without an orchestrator in the middle?
A callback step is literally a step within your SageMaker pipeline definition. When the pipeline reaches that step, SageMaker makes an external call in this case, utilizing the AWS SDK to start the AWS Glue workflow. Along with that start command, SageMaker generates and passes a unique cryptographic token.
Okay, and then SageMaker just goes to sleep.
Exactly. SageMaker enters a paused state. It doesn't poll, it doesn't consume active compute, it just waits. Meanwhile, your Glue job runs its heavy ETL. When the Glue job successfully finishes, the final step of the Glue script utilizes that unique token to make an API callback to SageMaker.
Using the SDK again.
Right. It says, I'm finished, here's the S3 URI for the output data, and here is my token. SageMaker validates the token, wakes up, and resumes the pipeline natively. You have achieved cross-service orchestration with 0 external state machines.
That is incredibly elegant architecture. It completely removes a layer of infrastructure. But let's look at orchestration from the other direction. What about triggering a pipeline from the outside world?
Always a fun challenge.
Here's the scenario. You have a third-party vendor. Every 3 to 4 days, at completely random times, they drop a massive, clean data set into your S3 bucket. The business requirement is that the moment that file lands, you need to initiate a retraining of your model to capture the latest trends.
This is where we see developers falling back on anti-patterns from 5 or 10 years ago. On the forums, you will see people suggesting that you set up an AWS Lambda function on a cron job to wake up every hour, scan the S3 bucket to see if a new file has been added, and if so, trigger the SageMaker pipeline.
Polling, the absolute enemy of cloud architecture.
Polling is terrible. You are paying for Lambda compute every single hour just to ask S3, is there anything new? 99% of the time, the answer is no. You are wasting money and adding operational overhead managing the Lambda code.
Okay, so my instinct would be to just put an S3 event trigger directly on the bucket that fires a Lambda function. So when the file lands, it triggers Lambda, and Lambda triggers the pipeline.
Which is definitely better than polling because it's a push model rather than a pull model. S3 natively pushes an event when the object is created, but you are still writing and maintaining a custom Lambda function just to act as a router between S3 and SageMaker. That's still unnecessary glue code.
Okay, so what is the modern event-driven solution that requires 0 custom code?
The solution is Amazon EventBridge. EventBridge is a serverless event bus that natively integrates with almost every service in AWS. When the vendor drops the file into S3, S3 natively emits a put object event directly onto the EventBridge default bus.
Okay, so the event is on the bus. What next?
You create an EventBridge role that listens specifically for that exact S3 bucket and that exact event type.
And the target of that role?
You set the target directly to your SageMaker pipeline ARN. EventBridge handles the routing, the payload delivery, and the triggering automatically. 0 custom Lambda code, 0 pulling compute costs. The infrastructure handles the orchestration natively based on events.
It's all about connecting the native managed services. Let's look at what happens after that pipeline successfully finishes. The model is trained. Now we have to manage the artifacts.
Model registry.
Yes. Scenario. You are at a massive enterprise. You don't just have one model. You have hundreds of data scientists across different business units building computer vision models for quality assurance, NLP models for customer service, and tabular models for forecasting. You have hundreds of discrete models sitting in the SageMaker model registry. The governance team comes to you and says, we need to organize this. We need to group these logically so teams can find them, but you cannot alter or duplicate the underlying artifacts because that breaks compliance lineage.
This is a phenomenal governance scenario, and the community reflex is almost always to rely on custom metadata. They say, just attach custom tags to the model packages. Tag it Vision Team A or NLP Core.
Why is tagging a governance nightmare in this specific context?
Tags are just key value pairs of metadata. They don't provide any structural or hierarchical organization. If you have 100 different data scientists, someone will tag a model NLP, someone else will tag it NLP in lowercase, and someone else will tag it natural language.
Oh yeah, the spelling variations alone will ruin searchability.
Exactly. Discoverability at scale becomes impossible. More importantly, relying purely on tags means you still just have one massive, flat bucket of models.
So what is the native feature inside the model registry to handle this securely?
Model registry collections. This is exactly what they were designed for. Collections allow you to hierarchically organize model groups. You can create a collection called Customer Service NLP and organize all the relevant model groups inside it.
But wait, The constraint was that we couldn't alter or duplicate the artifacts. If I move a model into a collection, doesn't that change its lineage?
What's fascinating here is the underlying mechanics of a collection. Collections are essentially organizational pointers. They are virtual folders. When you associate a model group with a collection, you are not copying the physical S3 model artifact.
Okay, so the artifact stays put.
Right. You are not mutating the artifact's internal metadata. You are simply creating a logical link. It gives you enterprise-scale discoverability without risking artifact integrity or compliance tracking.
Excellent. And let's say a senior data scientist finds the model in that collection, evaluates it, and wants to push it to production. We need a manual approval workflow. I don't want an automated script deploying unverified models.
Again, developers will try to build external tracking tools for this. They will try to use Jira APIs or custom databases to track approval states. Keep it native. The model registry has an approval status built right in.
How does it work?
When the model version is registered, it defaults to pending manual approval. You use the AWS SDK like Boto3 in Python to simply change that model's status to approved. That exact state change natively emits an event to EventBridge, which can then trigger the deployment phase of your CI/CD pipeline. The registry is the source of truth.
Okay, the model is approved. We are ready to deploy. This brings us to what I consider the most unforgiving part of the exam, the inference matrix. Deploying the model to production is where the architectural constraints get incredibly strict, and if you choose the wrong endpoint, you either break the application or bankrupt the department.
This is arguably the most critical operational skill for an ML engineer. You have to perfectly match the physics of the workload to the architecture of the endpoint.
Let's run a gauntlet of scenarios here. Scenario A. You have a retail recommendation engine. The traffic patterns are highly unpredictable. You get massive bursts of traffic during flash sales and very little traffic at 3 a.m. The payloads are tiny, maybe 1 kilobyte of user ID data, but the latency constraint is strict. The recommendation must load in under 100 milliseconds.
This is the textbook definition of a SageMaker real-time endpoint. You need immediate, synchronous response times.
But what about the traffic bursts?
To handle the unpredictable bursts without over-provisioning compute, you configure auto-scaling policies based on a metric like invocations per instance. When the flash sale hits and the invocations spike, the endpoint automatically scales out horizontally, adding more instances behind the load balancer to handle the thousands of tiny, fast requests, and then it gracefully scales back down when the sale ends.
Simple enough. But now let's look at scenario B, what I call the asynchronous heavyweight. You are working for a biotech firm. You have a massive genomic sequencing algorithm. A researcher uploads a 100 megabyte payload of raw genetic data. The algorithm requires intense compute and takes several minutes to run a single inference.
This is where architectures violently break. The forum trap is usually to say SageMaker can't handle a 5-minute process, so extract the model, deploy it to a massive EC2 instance, put it behind an application load balancer, and manage it yourself.
Or they try to force it into a real-time endpoint and the client application just crashes.
Right, because real-time endpoints have hard physical limits. A SageMaker real-time endpoint is built for synchronous HTTP requests. It typically enforces a strict 60-second timeout limit.
So if it takes 61 seconds, the connection just drops.
Exactly. If the model takes longer than 60 seconds to process, the load balancer drops the connection. Furthermore, real-time endpoints typically have a 6 megabyte payload limit. If you throw a 100 millibyte genetic payload at a real-time endpoint that takes 5 minutes to process, it will immediately reject the payload, and even if it didn't, it would time out before finishing.
So what is the purpose-built solution?
SageMaker Asynchronous Inference. It is designed entirely around decoupling the request from the response.
How does the async architecture physically differ from the real-time architecture under the hood? Like, where does the 100 MB file go, if not to the endpoint?
Instead of sending that massive 100 MB payload directly in the HTTP request to the endpoint, your client application uploads the payload to an S3 bucket. You then send a lightweight API call to the async endpoint that essentially just says, hey, here is the S3 URI where the data lives.
So you're just passing a pointer.
Exactly. SageMaker receives that URI and places a pointer into an internal managed queue. Think of it like an internal SQS queue that AWS manages for you. The endpoint instances continuously pull that internal queue.
What happens to the client? Are they just waiting?
No, the synchronous connection to your client is already closed. The client isn't waiting. When an instance is free, it pulls the pointer, downloads the 100 MB file from S3, and begins processing. The model can take 5, 10, 15 minutes to process the genome.
And how do they get the result back if the connection is closed?
When it finishes, it writes the output back to S3, and it natively fires an Amazon SNS notification that says, "I'm done, here's your result." It completely circumvents the HTTP timeout and payload constraints.
That is brilliant systems engineering. Okay, scenario C, the intermittent workload. You have an internal financial forecasting model. It is heavily utilized by the finance team for exactly 2 hours a day, right before the market closes. The other 22 hours of the day, it receives absolutely zero traffic.
If you deploy that to a real-time endpoint, you are paying a massive hourly rate for an EC2 instance to sit completely idle for 22 hours a day. That violently violates AWS cost optimization principles.
So the solution is SageMaker Serverless Inference.
Correct. With serverless inference, you do not provision or manage the underlying instance types. AWS manages a massive pool of compute natively. When a request comes in at 2 p.m., AWS dynamically provisions the compute, loads your model container into memory, runs the inference, and returns the result. When the traffic stops at 4 p.m., the infrastructure scales entirely back down to zero. You only pay for the precise milliseconds of compute duration you actually consume.
But wait, here's where it gets really interesting. This leads us directly into a massive battleground scenario that I see confusing everyone on the forums. An ML engineer deploys their model to a serverless endpoint to save money. But during the first few requests of the day, they notice that the latency is drastically higher than their baseline expectations.
The dreaded cold start.
Exactly. They suspect they are experiencing a cold start. The physical time it takes for AWS to provision the serverless hardware and load the massive model artifact into memory because the endpoint had previously scaled to zero. The engineer needs to prove this to management using CloudWatch metrics. You look at the forums, and developers are fiercely arguing. Half of them are screaming, "Look at the model setup time metric, that proves the cold start." The other half are saying, "No, it's model loading wait time. Model setup time is a trap." Let's settle the debate right here. Who is right and why?
The ones arguing for model loading wait time are absolutely correct, and this is a crucial, nuanced detail for the MLA-C01 exam.
Why does model setup time even exist if it's the wrong answer? Like, the name sounds exactly like what a cold start is.
Because model setup time measures something entirely different. It is a metric specifically used for multi-model endpoints.
Wait, what's a multi-model endpoint?
A multi-model endpoint is an architecture where you have a single EC2 instance hosting potentially dozens or hundreds of different models in the same container. When a request comes in for Model B, but Model B isn't currently in memory, SageMaker has to pause, reach out to S3, download Model B's weights, and load them into the container's RAM. The time that specific download and setup takes is model setup time.
Ah, so the underlying server instance is already running. It's just swapping the model files in and out of memory.
Exactly. But serverless inference is fundamentally different. When a serverless endpoint scales from 0 to 1, it isn't just downloading a model, it is waiting for the entire AWS serverless control plane to allocate the underlying compute resources, launch the container, attach network interfaces, and initialize.
That's a lot more than just swapping a file.
Right. The specific CloudWatch metric that tracks the time a request spends queued waiting for that serverless infrastructure to provision and the model to load is model loading wait time. Understanding the mechanical difference between these specific SageMaker CloudWatch namespaces is often the difference between passing and failing.
Okay, we've navigated the inference matrix. We've deployed the model perfectly. It's running, it's scaling. We're done, right?
Not even close. Now we enter day 2 operations. If you deploy a machine learning model to production and just walk away, you are deploying a ticking time bomb.
The world changes, and your model degrades. Let's look at a scenario. You deployed a highly accurate XGBoost model designed to predict customer churn. It's been running flawlessly in production for 6 months. Suddenly, the product team alerts you that the F1 score, the harmonic mean of precision and recall, which is our key accuracy metric for imbalanced data, has dropped significantly. The underlying data pipeline isn't broken. The code hasn't changed. The servers are healthy. What happened?
What you are experiencing is called concept drift, and this raises an important question that you must master for the exam. What is the mechanical difference between data drift and concept drift?
Break it down for us.
Data drift is straightforward. It happens when the statistical distribution of your input features fundamentally changes. Let's say your model was trained on a user base that was primarily 18 to 25 years old. Over 6 months, a marketing campaign successfully targets older demographics, and suddenly the live traffic is mostly users aged 35 to 40. The actual shape of your incoming data has shifted away from your training baseline. That is data drift.
Okay, that makes sense. The data itself looks different. What about concept drift?
Concept drift is much more insidious. Concept drift means the underlying mathematical relationship between your features and your target variable has changed in the real world.
Give me a real-world example of that, because that sounds abstract.
Think about a model predicting housing prices. You train a model in a booming economy. The model learns a core concept. A 2,000 square foot house in a specific zip code predicts a sale price of $800,000. Then a massive economic recession hits. Interest rates skyrockets. Suddenly, that exact same 2,000 square foot house in that exact same zip code only sells for $500,000. The input data, the square footage, and the zip code looks entirely normal. The distribution hasn't changed. But the concept of what determines value in the real world has fundamentally shifted. Your model, trained on the old reality, continues to confidently predict $800,000. It is completely blind to the new reality.
That is terrifying from a business perspective. So how do we catch this before it ruins the company? The exam loves to test your ability to differentiate between the three major AWS observability tools: Model Monitor, Clarify, and Debugger. They sound similar, but they do vastly different things. Let's do a deep dive into each.
Let's start with SageMaker Model Monitor. Model Monitor is your day 2 operations watchdog. Its primary job is to detect exactly what we just discussed: data drift and model quality degradation.
How does it mechanically know that drift has occurred? Does it just guess?
No, it relies on baselining. Before you deploy, you run a baseline job on your training dataset. Model Monitor analyzes the statistics of your training data, the mean, the variance, the distribution of categorical values, and generates a constraint file.
So it creates a mathematical fingerprint of what normal looks like.
Exactly. Then, in production, Model Monitor intercepts the live incoming inference requests and the model's predictions. It continuously compares the statistical shape of the live payload data against that original constraint file. If your demographics suddenly shift, or if the distribution of a feature wildly deviates beyond a standard deviation threshold, Model Monitor flags the violation, emits a CloudWatch metric, and triggers an alarm.
Okay, so Model Monitor is watching the data distributions in real time. What about SageMaker Clarify?
Clarify is your specialized tool for bias and explainability. You use Clarify to detect underlying patterns that might skew accuracy across different protected demographics.
How does it measure that?
It looks at metrics like disparate impact or difference in proportions. For example, if you have a loan approval model, its overall accuracy might look like a perfect 95%. But Clarify will dig deeper and might reveal that the model is disproportionately rejecting a specific age group or zip code at a much higher rate than others, even though the overall accuracy seems fine.
So it catches the hidden biases.
Right. But Clarify's real power is feature attribution, often using Shapley values, SHP values. It explains why the model made a specific prediction by calculating the marginal contribution of each individual feature to the final output. It tells you this loan was rejected primarily because of the debt-to-income ratio and secondarily because of the credit history length. It opens the black box.
Okay, so Monitor is for drift, Clarify is for bias and explainability, and finally, SageMaker Debugger.
Debugger is the odd one out here because it is primarily used during the training phase, not in production. Debugger peers directly into the active training loop to catch computational anomalies in the deep learning tensors.
What kind of anomalies, like code errors?
More like mathematical errors. Things like vanishing gradients or exploding gradients in a neural network. Or a classic scenario. You're training a model, and Debugger alerts you that the validation loss is oscillating wildly. The loss goes down, then shoots back up, then down again.
If Debugger catches that oscillating loss, what is the architectural fix I need to apply?
If we look at the math of gradient descent, an oscillating loss almost always means your learning rate is too high. The algorithm is taking steps that are too large, and it is literally overshooting the optimal minimum point in the loss landscape, bouncing back and forth across the valley. The immediate fix is to decrease your learning rate or implement a learning rate decay schedule. Debugger catches the math error before you waste hours of GPU compute.
Okay, that perfectly clarifies the big three. Monitor for production drift, Clarify for bias, Debugger for training tensors. But let's go back to our churn model. Model Monitor has successfully detected that concept drift has occurred. The world changed, the F1 score plummeted, and Model Monitor emitted a CloudWatch alarm. We know the model is broken. How do we automate the fix? Remember the golden rule? Least operational overhead. I do not want to manually trigger a training job every time the market changes.
This is where we bring it all together into a closed-loop system using EventBridge.
Walk me through the workflow.
When Model Monitor detects the drift, it emits a metric to CloudWatch. You configure a CloudWatch alarm to monitor that specific metric. When the along state changes to alarm, that state change is naturally captured by Amazon EventBridge.
And then EventBridge targets the pipeline.
Yes. You configure an EventBridge rule that says, when this specific drift alarm fires, immediately target my SageMaker pipeline. The pipeline automatically wakes up. It pulls the newly collected production data from S3, initiates a new training job to capture the new market reality, evaluates the new model against the old one, registers it in the model registry, and deploys it to the endpoint.
A completely automated, self-healing, closed-loop retraining pipeline with zero manual intervention. That is the AWS well-architected dream right there.
It really is. It's beautiful when it works.
All right, we are entering the final stretch, and we have to talk about the generative AI frontier. The MLA-C01 exam is evolving rapidly, and it is heavily integrating Gen AI concepts, specifically around Amazon Bedrock.
This is the fastest evolving part of the AWS ecosystem, and it is exactly where developers bring the most dangerous outside misconceptions. Because the technology is so hyped, people think they need to build everything from scratch to prove they know how it works.
Here's the scenario. Your enterprise needs to build an internal chatbot. The employees need to be able to ask complex technical questions, and the chatbot must answer based on hundreds of proprietary internal technical documents, PDF manuals, CSV datasheets, and text logs that are securely stored in an S3 bucket. These documents are updated daily by the engineering teams.
This is a classic Retrieval Augmented Generation architecture, or AAG. You need the LLM to synthesize answers based on your private, constantly changing data.
But if you look at the forums, people suggest architectures that are computationally and operationally devastating. You will see people say, extract the text from the PDFs, load it all into a custom Amazon Neptune graph database, and write complex traversal queries to feed the LLM. Or, even worse, they say, take an open-source LLM like Llama, spin up a massive cluster of GPEC2 instances, and fine-tune the entire model from scratch on the company PDFs.
Those are massive, costly anti-patterns. Let's tackle the fine-tuning trap first. If we connect this to the mathematical reality of large language models, fine-tuning is a computationally expensive process designed to alter the neural network's weights to change the behavior, style, or tone of a model.
Wait, so it's not for teaching it new facts?
No. You fine-tune a model if you want it to speak exclusively in perfectly formatted JSON for a medical application, or if you need it to adopt a highly specific corporate tone. You do not fine-tune a model to inject daily factual updates.
Why not? Because the facts change tomorrow.
Exactly. If you bake factual knowledge into the weights of the neural network today and that technical manual gets updated tomorrow, the model is instantly obsolete. You would have to launch another massively expensive fine-tuning job just to update a single paragraph. Furthermore, fine-tuning risks catastrophic forgetting, where the model loses prior knowledge while learning the new facts.
So fine-tuning is out for factual retrieval. What about the Neptune graph database suggestion?
Amazon Neptune is a highly capable graph database designed for mapping relationships like social networks or fraud rings. It is not a vector database optimized for semantic search and high-dimensional embeddings. The well-architected, least operational overhead solution for this entire scenario is a managed service called Amazon Bedrock Knowledge Bases.
Break down the mechanics of knowledge bases. Why is it the perfect fit, and how does it replace the custom RAG pipeline?
Building a RAG pipeline from scratch is incredibly difficult. You have to write code to extract the text from the PDFs. You have to write chunking algorithms to break the text into smaller pieces so they fit into the LLM's token limit. You have to call an embedding model to convert those text chunks into high-dimensional numerical vectors arrays of floating point numbers. And then you have to provision and manage a vector database to store those numbers and perform cosine similarity searches.
That's a massive amount of infrastructure and custom code.
It's a nightmare to maintain. Bedrock Knowledge Bases handles that entire pipeline serverlessly. You literally just point the knowledge base at your S3 bucket containing the PDFs. AWS automatically ingests the documents. It natively chunks them. It calls an embedding model, like Titan text embeddings, to vectorize the chunks. And it stores them in a fully managed vector store, often utilizing an OpenSearch serverless index under the hood, but entirely abstracted away from you.
So I just point and click, and the pipeline is built.
Yes. When an employee asks a question, the knowledge base automatically vectorizes their query, calculates the semantic similarity against the vector store, retrieves the most relevant technical chunks, and passes them seamlessly into the prompt window of an LLM like Claude to generate the final grounded answer. You wrote zero ingestion code, you managed zero chunking scripts, and you provisioned zero database instances.
That is the ultimate example of putting the developer hammer down and letting AWS do the heavy lifting. But let's add one final constraint, because the exam loves to test security posture. Let's say the application making the API calls to Bedrock is running on EC2 instances located in a private, isolated subnet within your VPC. The strict corporate security policy dictates that this traffic must remain completely private. It cannot traverse the public internet, and you cannot use a NAT gateway.
A very standard, highly secure enterprise constraint.
The trap here is developers saying, oh, just deploy the Amazon Bedrock service directly into the private subnet so it shares the same network.
Which is architecturally impossible. Amazon Bedrock is a fully managed serverless AWS service. It lives out in the AWS Global Service Network. It does not live inside your personal virtual private cloud. You cannot physically place it in your subnet.
So how do you securely connect your isolated private EC2 instance to a global AWS service without hitting the public internet?
You use AWS Private Link through an interface VPC endpoint.
Explain the routing mechanics of Private Link. How does it bridge the gap?
When you create an interface VPC endpoint for Bedrock in your private subnet, AWS literally drops Elastic Network Interfaces ENIs with private IP addresses directly into your subnet. These IPs act as a secure local doorway.
Okay, so the EC2 instance thinks Bedrock is right there in the subnet.
Exactly. When your EC2 instance makes an API call to Bedrock, it sends the traffic to those local private OPs. AWS Private Link then routes that traffic entirely over the internal AWS Global Network backbone directly to the Bedrock service. The traffic never touches the public internet. It never requires an internet gateway. It completely satisfies the strict security constraint while allowing you to access the managed GenAI service.
Private Link is always the answer for secure private access to AWS managed services, whether it's Bedrock, S3, or SageMaker APIs.
If you see private subnet and AWS service, look for Private Link.
Okay, let's take a step back and look at the massive landscape we've covered today. We've gone from lake formation data aggregation through the physics of FSX for Lustre storage bottlenecks. We've eliminated custom orchestrators with callback steps and EventBridge. We've navigated the hard limits of real-time versus async inference. We've broken down the mechanics of concept drift, and we've deployed serverless RAG architectures with Bedrock knowledge bases. If there is one core unifying theme we want you to take away from this deep dive, it's that the MLA-C01 exam is fundamentally testing your operational overhead radar.
That is the perfect way to phrase it. It is an operational overhead radar.
When you're reading a scenario on the exam, if an answer requires you to manage the underlying compute infrastructure like spinning up EC2 fleets or EMR clusters, it is almost certainly a distractor. If an answer requires you to write custom integration code like complex string matching loops, pulling Lambda scripts or manual step function state machines, it is almost certainly a distractor.
You have to fight the urge to build it yourself.
Look for the native integration. Look for the managed service. Look for data wrangler, pipelines, model registry collections, and Bedrock knowledge bases.
This raises an important question, though, for anyone building a career in this space. As AWS continues to relentlessly abstract away the heavy lifting, as tools like Bedrock replace custom vector pipelines and SageMaker pipelines replace manual orchestration, what is your actual value as a machine learning engineer? If AWS is doing all the heavy lifting, what are you getting paid for?
That is a provocative final thought. I mean, if we aren't writing the custom algorithms and building the infrastructure from scratch, what happens to us?
The role isn't disappearing. It is shifting up the stack. You are no longer just a model builder sitting in a silo writing Python in a Jupyter notebook. You are becoming a systems architect. Your supreme value now lies in understanding the complex mechanics of how to snap these massively powerful managed components together securely, efficiently, and cost-effectively.
It's a completely different mindset.
It is. Consider how the integration of your models into the broader enterprise software lifecycle, the automated retraining, the drift detection, the asynchronous queuing, is now just as critical as the hyperparameter tuning of the model itself. The core engineering challenge isn't purely in the math anymore, it's in the architecture.
It's moving away from trying to build a complex X-ray machine from scratch with your bare hands, and instead learning how to orchestrate a massive interconnected system to diagnose the problem instantly.
Navigate the complexity with the right architectural tools. Don't build the hammer if AWS hands you a nail gun.
And on that note, we'll leave you to your studying. Trust the managed services, watch your operational overhead, and good luck on the MLA-C01. See you next time on The Deep Dive.